Greetings. This is week one of ENE 350, a short video version of it. And we're just going to go over some of the things that we covered last week. So the first thing that we talked about was what this course, computer organization, that is designed for and what it really aims to accomplish. And so ENE 350 is the first computer class in the ECE undergraduate curriculum, not counting 244 and 245 because those are combinational and sequential circuit design classes that deals with the organization of computers. And it kind of aims to cover the following subjects. Let me just make a quick correction here. And then go back to the presentation. So we're going to talk about the organization of a sequential computer. In fact, we did that last week to some extent, and we call that the von Neumann architecture. And then we will cover basic computer operations and instruction formats and instruction processing. And then we'll talk about not so much the structures of memory, so in this set of slides, but the addressing techniques we might have in caching and paging thoughts. That's in general that we're going to cover. Assembly and machine language programming, bootstrapping, I/O processing, interrupts in kernels, pipelining and instruction pipelines. Those are roughly the things that we're going to cover in ENE 350. So in this first week of classes, we began by von Neumann computer architecture to just get a good sort of firm understanding of what it is that a computer organization entails. This is where it all began. Von Neumann is considered to be the father of, I guess, modern age computers. And his idea was the so-called store program concept. And what he basically does, he thinks of programs residing in a computer memory. This could really sound very conventional and very usual now, intuitive, but at the time that he considered this and he introduced it, it was not at all clear that this would be the way to go. So programs reside inside a memory as a sequence of instructions, and let me just take out a couple of words here, and they're executed one instruction at a time. Now we use a program counter to keep track of the next instruction to be executed, and that's very helpful. This is really the crux of von Neumann idea. And instruction register is also needed to hold the instruction during its execution. So I guess by way of a block diagram, we can view a von Neumann computer as having basically three boxes. In the center is what we call a central processor unit that happens to have registers and an arithmetic logic unit. And it interacts with memory, which happens to contain programs and data on which we execute our instructions. And so that's one side of the CPU. On the other side of it, the CPU also interfaces with some I/O processing, which in the least has to have a keyboard for us to type in our programs and data, and then a screen for us to visualize, to see what we're typing and what we're entering, as well as what the computer does after we process our programs. So this is the most basic, I would call, a von Neumann computer. It could really branch out from here to a lot more complicated representations, but this nonetheless gives you the basic idea. So the instructions in a von Neumann computer come in numerous formats, but they all have a field that is common to all. all of them. It's called the opcode. The opcode defines the operation of an instruction that a computer would execute when it processes that instruction. The rest of the instruction, or an instruction format, refines the interpretation of the opcode and specifies the operands on which the operation is performed. So operations are opcoded or coded into this portion of the instruction which is called the opcode, and that can be further refined by way of additional fields here, and that same field can also be used to specify the operands on which the opcode, the instruction that is described by this opcode, executes. It may also have addresses. So some two examples here, like add a comma b. Add is the opcode, a and b are the operands, or subtract a, b with brackets around them. Subtract the operand that is held in address a. Rather, it's subtract the operand that's held in b from that is held in a. That is, a and b are now sort of placeholders where our operands reside. So this bracket notation sort of separates the interpretation of the opcode in the two examples we have here. The first one uses a and b as operands, the second one as placeholders or addresses for those operands. So the address fields in instructions can also have numerous forms, and these forms characterize the operation style of a CPU. We talked about this last week, so we sort of broadly classified our von Neumann architectures into four different classes. 3 address machines, we call them memory machines, 2 address machines, load store machines, 1 address machines, accumulator machines, they're also called, 0 address machines, and stack machines, we also call them. Now we're going to talk about stacks later in the semester. So examples are here, like add a comma b comma c. These are placeholders, and so what that really means, either a would have the sum of the 2 operands held in locations b and c. This could also have the following interpretation, where c becomes the placeholder for the result, whereas a and b are the placeholders for the 2 operands that must be added to produce the sum that will then ultimately go into c, location c, that is. And then in the case of a 2 address machine, we deleted the c. Now we're down to 2, and the rest of it's similar. So a either takes a plus b, the contents of those 2 locations, or it's b that takes the contents of those 2 locations added together. So we kind of lose at the end of this, if you notice, either a or b. Whatever was there is overwritten by the sum of the 2 operands that are held in these 2 locations. Now, a 1 address machine will be also called an accumulator machine, simply uses an implied location, which will be called the accumulator, as the place of accumulating results. So here we have add b, and a is the implied register here, that is our accumulator, and the sum of the 2 operands that are held in these 2 locations are then put into the accumulator. Now in the 0 address machine, which is also called a stack machine, you don't really specify any address, not even one. And so like a typical add instruction will have no operands, and all that would mean, take a stack memory would then have top 2 locations which are added together and then put into the top location. And so that's a process. Now we could also have 0 address machines, as we shall see in just a little bit, without using stacks. In fact, VESP has that very mechanism where this add instruction does not take any operands, because it also has something we call a co-accumulator, and it's also implied. All right, so let's go a little more specific into VESP 1.0. It is the acronym for Very Simple Processor. It's just an example that is really designed. It serves no other purpose except to demonstrate to you how a von Neumann processor actually operates. So VESP10 is not the end. It is just an example of a von Neumann processor. It is a hybrid machine. Some instructions have a 0 address format. Some have 1, and one has 2. Its instruction repertoire is really small. It has only 8 instructions. It uses a 16-bit instruction format. The leftmost 3 bits of this instruction format specify the opcode. The remaining bits are either left unused or they specify an address. One of the instructions, and we call that move, is defined by 2 16-bit words, back to back, or one after the other. Its memory, the memory of this machine, VESP 1.0, consists of 65,536 locations. This is really somewhat virtual in that we don't necessarily have those many locations for all instructions because of the limitations of the instruction format we have. But in some cases, you could actually use up to 16 bits. So we can technically say this machine has potentially 65,536 locations to address. And it has a 16-bit program counter, so you can actually go through each and every one of those 65,536 locations, except the first 2, I should say, which are really reserved for the accumulator and the co-accumulator of this machine. You can write a program that could take up that much space. So the instruction register is where the next instruction will be held. The program counter is, like as in any von Neumann architecture, will point to the next instruction to be executed. Here's the table that we had also made in class, and these are the 8 instructions, and these are the opcodes in binary, and these are the actual operations. So add adds, complement complements, load actually loads from memory into let's see, what this does, it's just a little bit erroneous the way I've written it. I actually have to put another bracket here so that the brackets are closed properly. And what it does, it just takes MAR and adds 1 to it, and that becomes the address from which the operand comes, and that goes straight into the location whose address is actually located in these 13 bits of address that we hold in the first 16 bits of the of this particular instruction. So the move instruction is a more generalized version of the same. It actually uses the second portion of the instruction, the second 16 bits, not as an operand, but as an address. As you can see that the M stepped in here a second time. There's an N and M and M here. There was only one M. Now, just thinking back to what I said earlier, I guess I should also add LOAD into LDA, that is, into the group of instructions that happens to have 2 16-bit words. So let me just make a quick change in there so that you get to be corrected also. LDA and move to, I guess I should say, and then say R. Alright, so these not have been, as you can see, proofed. I'm just speaking to them as I prepare them. One little quick change here, just a full stop there. Okay, so we move on, and so that's the other instruction right there, the second instruction that uses 2 16-bit words. And the next instruction is a jump instruction, not JPS, just jump. And these corrections sometimes help because otherwise you may just look at this, stare at it without really knowing what these mnemonics and other terms are. So we just made a correction to suggest to you that this is called a force jump. There's no condition on this jump. It just jumps to the location that is indicated by the instructions address field. That's where we want to jump to. JEZ is like jump, except that we need to check if AC is equal to 0. Now, there is a 0 flag, as I said in class, that we use to actually test for the AC being 0. But here I've written it more explicitly so you know that it is the accumulator that's actually causing this jump if it is equal to 0. And jump positive is when AC is greater than 0, and then the halt is reset. And reset, it means like, stop the machine and reset it for another run in case that we want to run another program. So this is how these instructions are organized. And now we want to talk a little bit about controllers because we did cover that in class last week. And so the controllers are those things that, the actual physical things that process instructions within CPUs. They are a part of every processor. The processor without a control unit will be difficult to imagine. So the behavior of a controller can be broadly described by the following sequence of steps, as I said. First, you want to fetch the next instruction, and then you want to decode it, execute it, and then repeat this process. So each of these steps will take one or more clock cycles to complete. Fetch step loads a new instruction from memory into IR. Decode actually uses the opcode, interrogates it to see what the instruction wants to do. And then the execute step carries out the actual operation specified or decoded in the prior step. In VESP, these steps take a very particular form. So we began talking about this last week, and then we also talked about this on Monday. So that will go into our week 2 coverage. But here I'll just simply mention a couple of things. So first of all, in VESP 1.0, programs and instructions, therefore, are stored in our memory, or in VESP's memory. And there are 2 registers, which we talked about already in class. MAR, Memory Address Register, and then MDR, Memory Data Register. Those are the 2 registers we use to access the locations in memory, to either write into it, into the memory that is, or read from it. Maybe I just fix something here. I could just say, right, access a location. Maybe that will just make it a little more precise for you, if you like. So that's what we do. And here's the pseudocode that actually describes the fetch process. Now we will talk about decode and execute in next week's video summary. But here we talked about this. So here's your first step. You load the instructions address, which is held in PC at any time, into MAR. And then you increment the program counter by 1 because you want to get ready for the next instruction. In case that's the one that you want to execute, you're not going to branch out to anywhere by way of a jump instruction or a conditional jump instruction. So then once you put that MAR, PC into MAR, you can actually do a read, which you do here. And then you take whatever goes into MDR. Remember, I just said here that we use MDR to write and read in and out of memory. So here we're reading. And then what gets into MDR then goes into IR. This completes the fetch process, as I just explained. So here is an actual sequential circuit representation of the same 3 steps. Initially we are at the rest state, so we spend a clock cycle to actually get ourselves into this particular next state where we do the copying of PC into MAR. And we have to, and the pulse is generated. By the way, this is called a one-hot design, because at any point in time, only one of these flip-flops will have their pulses up, not more than one. And so in this one-hot design, the first step, after we leave the rest step and then come into this step, is where we make this transformation, that is copy PC into MAR and then PC to add an increment to PC by 1. These two steps take place at the same time. Whether I write this at the top or at the bottom, it doesn't really matter, because all this does, once we get to be here, excuse me, this pulse will affect these steps, these changes. And at the end of the clock cycle, that is by the time we get here, these will be conditioned. MAR will have the PC, and PC will have PC plus 1, a prior value of PC plus 1 in it, and that we will have right here, because this is when the pulse goes up to make this change, and this flip-flop is kind of like separating the next step from this, meaning that in the one clock cycle we go from here to here. This process has been completed. Now we have MAR and PC, PC and MAR rather, and then we use that fact to access our memory. Now, one thing I just didn't write there was actually to say I want to, let's see how I do it before. It's going to be a little complicated, but I'll be able to manage. So I'll just say read 1. Okay, so that takes care of right there. So we do read 1 also, as we did it in the prior slide. And so now that we did this, and then we separated this process by a clock cycle, when we get to here, we know that MDR has the instruction, and we push it into IR. So that completes the fetch process. Now this is our rest state. We're going to come back to this, having done something, so that whatever we do in the end will also be separated by a clock cycle by whatever we do in this step. So all of this will be just looped back when we complete our execution, decode and execution stages. Okay. And so this is really pretty much what we covered last week, and let me just summarize one more time. We stated the goals of the course. We introduced the von Neumann architecture. We described the instruction formats, addressing modes as well. We explained instruction processing. We then illustrated the von Neumann architecture using VESP 1.0. And finally, we transformed the fetch step among the 3 steps we have to process instruction into an actual sequential circuit. So those are the things we did. And here's a very simple homework assignment for you to just warm you up a little bit. So in this case, in this very first assignment, you're going to be just doing a simple VESP program just to warm up. And I want you to write a VESP 1.0 program in hexadecimal machine code to compute the following expression, arithmetic expression: 23 plus 12 minus 116 plus 17 minus 295. I want you to use the CMP instruction to carry out your subtractions. Now, you all learn in ENE 244 what we call 2's complement arithmetic. So I'm not going to obviously cover it in this class because I assume that you've covered that, or your professor did, in ENE 244. So that's just assumed on your part. If you are not too fresh on that, you may want to brush it up. Just simply go back to your notes or textbook and see if you could just study how 2's complement arithmetic works. And then once you write the program, I want you to run it and verify that its computation is correct. So this is your first homework problem, and I guess we could just point these also. We can assign them points. So let's just make this 10 points. And let's also make this 10 points so that your work is equally divided between 2 parts of the homework assignment. So I believe this completes our coverage, the video coverage of our first week. And what I will try to do, I can't really promise that I'll be able to do this every time, but in the early going at least, I should be able to give you some push by way of these video representations of what we've done a week prior, so that you get to be motivated to to complete your understanding of the material that we cover. So I'll see you later today. Until then, take care, and we'll see you.